Hey everyone, welcome to another Science Saturday. I'm your host, Noah Mugen. I hope you've all had a warm, wonderful February and a happy Valentine's Day. It's great to see y'all again. Today, we're going to be going over the science of momentum, and I'm going to quickly go over the materials that we'll be using in today's experiments. Now, if you don't have all these, don't worry, it's easy to follow along.
Today we're going to be using a small ball, a big ball, some sort of powder, maybe sugar or flour, an easily breakable object like a candy cane or maybe a cracker, and a pillow.
This has been one of the coldest Februaries on record for our area. I mean, look around me, there's snow everywhere. If you didn't know, this isn't normal. This has been a wonderful chance to hop in some snow, have a snowball fight with some snowmen, then head inside to jump in some blankets and sip some hot chocolate. And actually, there's a chance for some scientific inquiry in that, even though it may not seem like it. For example, when you jump in some snow or hop under the covers, why do you come out unscathed and just ready to relax? But if you try that same stunt on some concrete, you're going to head to the hospital. Well, that's the question that we're going to be answering in today's video. To start, we're going to have to go all the way back to our good friend, Isaac Newton. You've probably heard of him. The story goes that one day, little Isaac Newton was sitting under an apple tree when an apple fell out of it and bonked him on the head, giving birth to his theory of gravity. While this isn't entirely true, Isaac Newton did make enormous strides in the fields of gravity, calculus, optics, and mechanics, and was one of the most, if not the most, influential scientists of the 17th century.
He was also interested in the quote-unquote science of alchemy and the search for the legendary Philosopher's Stone, but that obviously never came to fruition and isn't relevant to us today. What we're going to be focusing on are Newton's laws of motion. In his 1687 work, Philosophiae Naturalis Principia Mathematica, Isaac Newton established 3 laws of motion that govern all objects. The first law states that every object moving at a constant velocity or at rest will stay at a constant velocity or stay at rest until some other force acts on it, say your hand pushing a ball. The third law states that for every action, there is an equal and opposite reaction. However, today we're going to be focusing on Newton's second law, which is commonly written as force equals mass, or m, times acceleration, or a.
Now, a force is any push or pull on an object. Think of gravity pulling you to the ground, or the force you put on a snowball when you throw it.
We're going to measure force in newtons, named after you-know-who.
And mass is the amount of matter in an object, basically how much stuff there is. The more mass an object has, the harder it's going to be to get it to move or stop moving, and the more gravity will pull in the object, aka its weight.
Mass is most commonly measured in kilograms, also written as kg.
And acceleration is an object's change in velocity over a period of time. Now, what is velocity, you might ask? Well, velocity is really just an object's speed in a certain direction. It's a vector quantity, meaning that it has both direction and magnitude. In this case, the magnitude would be the speed of the object. Say you might be moving 5 miles per hour, that would be your speed, heading north, that would be your direction. Since acceleration is just a change in velocity, when you accelerate, you can either change direction, you can go faster, or you can go slower than you were before.
We measure velocity as a change in meters aka how far you're going, divided by the change in time, in seconds. Basically, how long it takes you to get there. Since acceleration is a change in velocity over a certain time, then we can measure acceleration as a change in velocity divided by seconds, aka the time it takes for that velocity to change. So in other words, acceleration can be measured as a change in meters over a change in seconds. Remember, that's velocity, that's how we measure velocity, divided by the change in seconds, also known as how long it takes for this to change. This can be also written as meters divided by seconds squared.
And we can actually show that force equals mass times acceleration with a simple experiment right here. For this one, all you're going to need is a large ball, a small ball, and some sort of powder. You can use flour or sugar. I'm using snow since it's all around me. If I were to drop these two balls from the same height, which would hit the ground first? Would it be the larger ball because gravity has a greater pull on it? Or would it be the smaller ball because the smaller ball takes less energy to get going? Well, it turns out that those two forces equalize and that the balls will hit the ground at the exact same time. In fact, any two objects, regardless of their size, will hit the ground at the same time if they're dropped from the same height, ignoring air resistance, of course. Since the balls hit the ground at the exact same time, we know that their acceleration, or the change in their speed in a certain direction, is going to be equal. However, this ball has a lot more mass than this one. And if force equals mass times acceleration, then it follows that if their accelerations are the same, then the one with the most mass will have the most force. And we can actually show that this ball has more force with a simple experiment right here. For this, you're going to gather two piles of powder. Over one pile, drop the small ball onto it. As you can see, it barely displaced the powder since this small ball did not have much force. Now, at the same height you drop your small ball from, drop the large ball on top of the other pile of powder. As you can see, this pile pretty much exploded since this ball carries so much more force. So when it hit that, all that force pushed the powder away. That's because force equals the mass of an object times its acceleration. Even though their accelerations were equal, this ball had much more mass. And as such, it was able to put much more force on the ground when it hit.
Now that's all well and good, but we can actually write Newton's second law in a different way. Since, remember, acceleration is equal to a change in velocity over a change in time, then we can actually write this as force on an object is equal to the object's mass multiplied by the object's change in velocity and then divided by the time it takes for that velocity to change. We can also rewrite this as the force of an object multiplied by the time it takes for that object to change its velocity is equal to the mass of the object multiplied by the velocity of that object.
Now, you've probably heard of the term momentum. Maybe your favorite football team has momentum to finally make it to the Super Bowl this year. Or maybe a race car has enough momentum to get across a rough part of the track. Well, in physics, momentum is a measure of an object's motion. It is equal to its mass multiplied by its velocity. In other words, momentum is equal to how much stuff is moving multiplied by how fast that stuff is moving. So if you have more stuff, or if that stuff is moving faster, then you're going to have a higher momentum. When I drop this snowball, the moment it hits the ground, its momentum will be its mass, the amount of snow that I have right here, multiplied by its velocity, the speed of the snow that is moving downward.
If you look back at our original equation, you can now write it so that the force on an object multiplied by the length of time that that force is put on the object is equal to its change in momentum. Because remember, momentum is equal to the mass of the object multiplied by its velocity. And here lies the answer to our earlier question. Why are pillows and snow easier to land on than hard concrete?
Whenever I drop an egg from some height, its momentum when it reaches the ground will be the same, regardless of what that ground is. When I drop this egg on the snow, it's going to take a lot longer to stop than if it hit the concrete, because in snow, the egg has to travel through the snow, slowly slowing down, while when it hits the concrete, it just has to stop immediately. Since the egg takes longer to stop on the snow than on the concrete, the force needed for the egg to stop is less, meaning that the egg is safe when it hits the snow, since the force is not enough to break its shell. Compare that to the concrete, where since it has to stop immediately, it takes a lot more force to stop the egg, meaning that that force will break its shell. Watch. The egg is fine. It passed through the snow slow enough that it was able to survive, and the force did not break its shell. Now, compare that to dropping the egg on the hard concrete. The egg smashed. It's on the ground, broken, because the force that the ground exerted on the egg was enough to smash its shell open, owing to the fact that the concrete just did not give the egg enough time to stop.
Now you can actually show this concept in a way that's not quite so messy as splattering an egg onto some concrete. All you're going to need for this is a pillow, some easily breakable object, say like a cracker, maybe some Lego pieces loosely stuck together. For me, I'm using a leftover candy cane from Christmas. To start off, you can place your pillow on the ground right in front of you. Then, drop your object, for me my candy cane, onto the pillow from about your head height. As you can see, my candy cane is perfectly intact, no cracks here. The pillow was pushed down by the candy cane and didn't stop it immediately, giving the candy cane enough time to stop that the force put on it wasn't enough to break it. Now, take your pillow away and drop the candy cane or whatever object you're using from the same height. As you can see, the top of my candy cane was snapped. Since the ground stopped the candy cane much quicker than the pillow did, the candy cane had more force put on it, and that force was enough to snap this candy cane.
And there you have it. Surfaces like blankets or snow are easier for you to fall on because your body takes longer to stop, and as such, the ground exerts less force on your body. Well, that about wraps up this Science Saturday. I had fun learning about the science of momentum, and I hope you did too. Stay safe, have a wonderful spring break, and I'll see you next month. Bye-bye!